Hi, I'm Fernando Pereira from UFMG, and today we shall talk about divergences. That's a phenomenon that hurts the execution of programs in the SIMT environment. As we had seen before, GPUs are divided into processing units that follow the SIMT environment. That means single instruction multiple data, if you recall. So we have several processing units operating on the same instruction. It's like a world where every person always does the same action. However, what happens when different people want to do different things? In this case, we have divergences. To understand what's a divergence, consider this program on the left. You can see its simplified assembly on the right side of the figure. So stop the video and read the program. You can see that we have a branch, and this branch depends on the thread identifier. So some threads might take the true path, and others might take the false path. What happens in this case? If threads take different paths, then we have a divergence. But divergences are just an illusion. In typical GPU implementations, what happens is that all the threads run the same instructions, but some of them do not write results back. So we have to blank out the results of some threads. And that hurts performance because we have work that's not useful being performed. As an example, let's see what happens once we run this program with different inputs. Take a look into the program. You might stop the video. That's a very naive program. It simply decrements every position of an array until we have zeros in the entire buffer. Can you see how divergences happen? The most serious divergences happen in this loop. You see, some threads might finish earlier than others. So here I have 5 different ways to initialize the loop. All these functions put in the array a set of numbers that tend to add up to more or less the same value. I mean, if you initialize the array and then sum it up, you might get more or less the same values. I say more or less because the 4th initializer uses random numbers. You can see the random function right here. Can you guess which initializer will yield the fastest run of the DEC2.0 kernel from the previous slide? Well, the first initializer puts in the array numbers in descending order. The GPU runs pretty fast on it. It took 16.250 seconds in my machine. The second initializer distributes the numbers evenly in the array. It runs a bit faster in my machine. The third initializer, on the other hand, is much worse. It sort of makes a comb in the array and takes twice as long as the second initializer. Can you understand why? Do you see that half the threads would be not doing useful work? The fourth initializer that puts random numbers in the array does slightly better than the third, but it's still much slower than the first 2 routines. And the last initializer is almost as good as the second. Well, it's the same basically. In both cases, there is only useful work being performed. And that was it for divergences. I hope you can take a look again into these examples that we did to make sure that you understand what's a divergence and how it works. In the next class, we start trying to find out when and where divergences might happen.